Welcome to the Extreme Broadband Engineering Cable 101 training series. In this session, we'll discuss return loss. The learning objectives for this session are: define return loss, understand what return loss is, learn how to calculate return loss, and review the return loss specifications. Let's get started. Return loss is the amount of signal that is reflected back towards the signal source by device due to an impedance mismatch. In this example, we're showing a two-way splitter with a forward signal feeding the input. Ideally, we'd like all the signal to flow through the splitter to both output ports. But in reality, some of the signal is reflected back towards the signal's original source. This signal is lost due to reflection. This reflection is known as return loss. The return loss is a factor with both the input and output F ports. In this example, we're showing return signals feeding into the output ports. Ideally, we'd like all the signal to flow through the splitter to the input port. But in reality, some of the signal is reflected back towards the signal's original source. Some of the signal is lost due to reflection. With return loss, the higher the value of the return loss specification is, the better. In this example, we're showing a two-way splitter with a return loss specification of 20 dB. A 20 dB return loss means that the reflected signal will be 20 dB less than the original input signal. On the input port, we're feeding with a signal of 20 dBmV. Most of the signal passes through the splitter, but a small amount is reflected back to the signal source. In this case, the reflected signal is 20 dB lower than the input signal and is at a minus 0 dBmV. 20 dBmV in, minus 20 dB return loss, for a reflected signal of 0 dBmV. So with return loss, whatever the value of the return loss specification is, the reflected signal will be that amount lower than the original signal. Let's look at another example. Here we're showing a two-way splitter with a return loss specification of 25 dB. A 25 dB return loss means that the reflected signal will be 25 dB less than the original input signal. On the input port, we're still feeding with a signal of 20 dBmV. Most of the signal passes through the splitter, but a small amount is reflected back to the signal source. In this case, the reflected signal is 25 dB lower than the input signal and is at a minus 5 dBmV. 20 dBmV in, minus 25 dB return loss, for a reflected signal of minus 5 dBmV. Let's take a look at return loss specification numbers. Here we're showing a specification sheet for our broadband digital splitter series, which includes two-way, three-way balance, and four-way splitters. On the left-hand side is a column labeled frequency. Here we break the frequencies into 7 different bands, starting with 5 MHz, going up to 1 GHz. Next to that is a column labeled min-max. These are the worst-case return loss numbers for these devices. These numbers are normally used by the engineers and designers of cable systems. The column next to that is labeled typical. These are the specification numbers that you would typically see from the majority of these devices in the field. You'll notice that each cell has 2 numbers. The first number indicates the return loss for the output port, and the second number is the return loss for the input port. This is also indicated on the far left. One area to make note is the specification for the output port in the 16 to 40 MHz bands. Here the return loss specification is better by 5 dB. Why do you think that is? We have to look at typical signal levels on the forward compared to the return. The typical forward signal levels feeding these devices are in the mid-teens to low 20 dBmV range. On the return, the typical signal range is much higher, around 35 to 55 dBmV. The higher the return loss at these frequencies, lowers the reflected signal back to the source that could cause problems. Return loss is affected by the F port terminations. All input and output ports need to be connected to a 75 ohm termination of some type. Output ports not terminated will result in poor input return loss, and input ports not terminated will result in poor output return loss. In this example, we're showing the poor return loss with the ports unterminated. Some poor terminations include ports with nothing connected to them, and cables connected to passive devices but not connected to the CPE on the other end. Once the proper terminations are in place, the return loss meets the device's return loss specifications. The impedance of a coaxial cable system is 75 ohms, and any variation from that will cause the signal to reflect back towards the signal source. Let's take a look at what happens to the reflected signal. In this example, we have a 75 ohm device connected to a two-way splitter through a length of coaxial cable that loses 2 dB. The input port of the two-way splitter has a return loss of 22 dB. The signal is fed from the 75 ohm device through the coaxial cable, and at the input of the splitter we have 20 dBmV. As we discussed previously, the reflected signal will be attenuated by the value of the return loss of the device, which in this case is 22 dB. We had 20 dBmV on the input, and now we subtract 22 dB from that for a result of a minus 2 dBmV. The reflected signal travels back through the coaxial cable and loses an additional 2 dB. So on the output of the 75 ohm device, we have a minus 4 dBmV. The 75 ohm device in this case also has 22 dB of return loss. So the signal is again attenuated by 22 dB and reflected back towards the splitter at a minus 26 dBmV. The signal again travels through the coaxial cable that has 2 dB of loss and arrives back at the input of the two-way splitter at a minus 28 dBmV. At this level, the signal is attenuated enough it should not cause any impairments to the original signal. The transition from a coaxial cable to a passive device will have a slight degree of impedance mismatch. This is unavoidable, but is minimized during the design and manufacturing process. Here we're showing some items that minimize return loss. The transformer inductance and capacitor value are closely matched to the best return loss on the lower frequencies. Mounting the capacitors on the printed circuit board improves the high frequency return loss consistency. Direct interface of the seizure pin to the PC board improves return loss consistency. The circumference premium digital contact improves the impedance continuity. The seizure contact inside the F connector is a critical component in the design for signal integrity. Multiple digital contacts increases the reliability of the connection between the customer and the network. Here we're looking directly into the circumference premium port and showing 4 points of contact on the center conductor. The curvature of the seizure conforms to the surface of the coaxial cable center conductor, maximizing contact area. There are 2 sets of 4 contacts for 8 points of contact with the center conductor. The coaxial structure of the seizure enhances the impedance continuity through the port interface. Let's review what we've learned in this training session on return loss. Return loss is the amount of signal that is reflected back towards the signal source by a device due to an impedance mismatch. The higher the value return loss specification, the better. Return loss is affected by the F-port terminations. The design and construction of the passive and active devices is essential for good return loss performance. Thank you for viewing this training on return loss. For additional training topics, see our website at www.extreme-broadband.com.